Okay, let's go ahead and answer these questions. So you could use the gas law equations, but I don't want you to use the gas law equations because you don't need to use the gas law equations. So in this question here, it's asking for the volume. You have three numbers, only one of them has a volume unit, that 12.3 liters. Great. So if you set up your calculation to put 12.3 liters here, that'll give you liters as your unit for your answer. And what we need to do is figure out what's going to happen here. So I've got a gas. This gas is a certain size, and it's at 40 millimeters of mercury. And the pressure increases to 60 millimeters of mercury. So what is what's going to happen to this gas's size if you increase the pressure on it? It'll decrease. This is Boyle's law. They're inversely proportional. Easiest way to think about it is I have a gas, it's this big, I squish it. What happens to it? It gets smaller. So I need to take my two pressure units and set them into this railroad track to give me a smaller volume number. So I just put 40 millimeters of mercury here and 60 millimeters of mercury here. The millimeters of mercury units cancel out. All I have are liter units. And it's whatever 12.3 is, divided by 8.2. Great. You probably need 3 sig figs though. 0. Okay. So the next one we can do sort of the same kind of stuff. The what's this question asking for? It's asking for the volume again, and what changes? So the pressure changes. There's a temperature unit in there. What are we going to do with it? In this case, it's just saying it's 25 degrees. Like hey, it's Thursday. Great. Okay, that doesn't affect the problem. So piece of ancillary information. You can change it into Kelvin if you want, but you're not going to use it because it didn't change. That's how you know you're not going to use something in one of these problems. If it didn't change or you weren't asked for it from a beginning, then it's not going to change and not necessary. So this is exactly the same problem with just one extra little piece of try to trick you information. So it's 3.6 liters here, and then 1 atmosphere in the numerator and 2.5 atmospheres in the denominator. And that gives me a smaller liter number, which is what? 1.44. Great. Okay. So I squished it. It got smaller. It's still 25 degrees. Doesn't matter. Next problem, we've got a volume, and we are looking for a volume, and we've got a temperature, and we've got a new temperature. So this is a Charles law problem. What do we need to do with temperature problems? Immediately go to Kelvin. So 273, 293, 273, 333. So this is at 20 degrees Celsius. It goes to 60 degrees Celsius. It's a certain size. So what happens to a gas that's heated? It gets bigger. It expands. So then I'm going to take 600 milliliters, and I'm going to put 333 Kelvin here, and I'm going to put 293 Kelvin here. And the kelvins will cancel, and what do I get?
681.9.
So 682? Where is that?
Would it be 682 when
Yep.
it gives us 600.0?
But there's only, it's 20.0, right? It's everybody's sig fig. Smallest one is the only one that matters. So 682 milliliters. So it got bigger. That's what we expected. So this next one is the exact same problem as the last one, right? Swapping over to Kelvin units, and so 273, 300 Kelvin, 273, 405 Kelvin. So I've got 900 milliliters, and it gets hotter, so it's going to get bigger. So I'll put 405K here and 300K here. And what do I get here? 1215. Okay. Yep. sig figs would have to take you to 1220, right? There's only 3.
Yeah.
You good with that? I didn't come up with it. It's just the way it is.
I'm just confused because then the other day you said you have to put more because what if it's a medicine for a patient or something? You were saying you have to be more accurate sometimes rather than not.
Nope, there isn't any.
Because yesterday there was one where we answered with more sick days.
I've not got this one.
No. Just steadfast. Sig figs. So there's 3 here. You can answer in 3, and that's it. The other way you can answer this question is you could write 1.22 liters. That would be okay. That would give you the correct answer. Everybody all right with me saying that? Milliliters turns into liters. Move the decimal place over 3 spots. That gives us liters, and then it would be 1.22.
So you're saying it could be either?
I'm saying that would be an answer. That would be a correct answer. If on a multiple choice exam you had that answer there, 1220 milliliters and 1.22 liters, which should you pick?
The milliliters.
The milliliter one, because it was given in milliliters. But if the only answer available to you is 1.22 liters, that's totally something that somebody would try to. I mean, it's a multiple choice exam, right? They gave you the answer. You know that right there is the answer to the problem. So the entire point after them trying to get you to answer the question is to try to trick you. Since they had to give you the answer, they got to try to make it a little bit more difficult for picking. So if the unit that you started with is given in one of the responses and the number associated with it is correct, pick that one. If it's not, think about a unit switch. They might have done that to you. Is this the same problem?
No, that one, that one's pressure.
Oh, we're looking for pressure here. Yep. Okay. So this one's Gay-Lussac, and we heated it up. So what's going to happen to the pressure? It's going to go up. 273, so 293, and then this is 303. And so I have 1 atmosphere, and I'm going to put 303 Kelvin here and 293 Kelvin here. And then atmospheres will be my unit. And what do we get with this? 1.03? That looks good to me. Okay. Complete the following single replacement reaction by entering the product states of matter and substances. Okay, so it's a single replacement reaction. What do I get on the other side? That's an absolute given, right? Manganese solid, that gets popped out. And since this is cadmium on this side, I can go ahead and write that as a solid. What else we got?
I said, cadmium, O2.
Nope. Why not? What's cadmium's oxidation state? 2.
I thought it was
It is a 2. What's oxygen's oxidation state? 2. So it's just CDO. Okay. How would you get, it doesn't matter. It's, what kind of compound do I have on the left? What's the name of that?
two.
No, it's manganese 7 oxide.
It's manganese 7 oxide. That is not a polyatomic ion. That is an ionic compound, and its charge on the manganese is 7 because that's what it would need to be to go with those 7 oxygens. You need a +7 on the manganese. So it's an ionic compound, so this guy will be a solid, and then over here, manganese oxide, solid. So if you looked on the solubility rules, they say oxygens are insoluble, and there isn't a manganese rule, and there isn't a cadmium rule. Balancing, what do we need? Looks like a 2 right there, and a 7 right there, and a 7 right there. Is that good? 2, 2, 7, 7, 7,
What
What did you call that? Manganese heptaoxide?
I did not say that, no.
What do you call it?
I'm not telling you, you tell me. What is it?
Okay, I already heard it. It was manganese 7 oxide.
Why is it manganese 7 oxide?
Because the oxide is.
Stop,
has-
tell me before that.
oh.
The first
Why is it
thing,
manganese 7?
yeah, tell me.
Okay,
what-
Because it's a metal,
Um,
and it has
no.
several, what,
It's an ionic compound.
okay.
So you said sept there. I heard that.
I said
Hept, well, okay, then
for the 7.
you really should have said
Yeah.
sept, because sept is 7 and hept, I'm sorry, they're both fine. Sept and hept are both 7. So why can't you say sept? Anybody?
That's covalent.
That's only for covalent compounds. You can't use that terminology. I would love it if we could. It would make all nomenclature super easy. You'd remember 10 prefixes and that'd be the end of it. But that's an ionic compound, so you have to name it the ionic way, so you have to say manganese 7 oxide. You're not allowed to use dimanganese heptoxide. That would make a hell of a lot more sense. It's just not happening.
Yeah.
Okay, so we got this thing, that's it? That's the whole thing? That's all we need to do?
Yes, balance.
Lame. Okay, I thought there was gonna be something else with that, but, all right. Great, so we got the states and we got it balanced and good to go. All right, so you started with 243 grams of copper and 200 of silver chloride. How many moles of each product will be made? Oh yeah, this is cool. I changed something and didn't change the other thing.
Was it supposed to be like a
So
single
we're supposed to find out how many
replacement
moles,
reaction?
right?
Um,
Would we want to know the moles?
that single replacement reaction with the cadmium and I copied and pasted stuff together, and that should have been the silver and the chloride and the copper, but that's fine. So what'd you guys do for this one? Since nobody emailed me and asked me what was up with this question in the last 48 hours that you had access to this question.
Are you saying
I
it doesn't
just-
make sense?
It
This question doesn't make any sense.
Oh,
I decided that it was a single replacement reaction,
That's
and then I made a chemical
lovely.
equation.
That is exactly what should have been the question before. It should have, where the cadmium and manganese 7 oxide are, that should have been copper and silver chloride.
That's what I figured.
Okay.
That's what we did, yeah.
When you do the reaction.
But moles of product, how do you know how many moles of product you're gonna make?
Or making the equation.
What equation?
Copper and chloride.
To do what? What's the copper and chloride equation? What'd you do? So this should have been Cu plus AgCl, solid, solid, turning into Ag solid plus CuCl2, solid. And then there should have been a 2 right there and a 2 right there. A 2 right there. All right, let's do that one more time. A 2 right there. We good with that? So there's my single replacement reaction. Okay. How many moles of each product are going to be made? All right. So I've got 243 grams of copper. And what is it, 63 point what? 546 grams of copper for 1 mole of copper, and then for every 1 mole of copper, it's let's do 2 moles of silver. Okay, and then I've got 275 grams of silver chloride, and then for every 1 mole of silver chloride, does anybody have that number? So 107.8682 plus 35.453 equals, so I get 143.321. So I got 275 divided by that number, that's that. So I got 1.92 moles, and then I got 243 divided by 63.546 times 2 equals 7.65 moles. Okay, so the limiting reagent is a silver chloride. We all okay with that? So what I need to do is do another railroad track with the silver chloride going to my other product. So then I'll do 275 grams of silver chloride, and then 1 mole silver chloride, 143.321 grams of silver chloride, and then 2 moles of silver chloride. What else we got? 1 mole of copper 2 chloride. So .96 moles of copper 2 chloride. We just stopped these railroad tracks one step early, right?
So what are you missing from that? From that question?
Oh, it should have been copper and silver chloride right there. The point of this is, what's the relationship between these two things here? What's the relationship between 0.96 and 1.92? That is exactly double that. How could that possibly be the case? Because there had better be double that, right? This is double the number of moles of this, because there are twice as many of those every single time this reaction happens. You don't get to see that when you put the grams down, because the grams are, since each one of those things weighs more or less than the other one, their relationship won't be the same, but the mole number will be the same every single time.
That's where you're counting, right?
I'm counting them, I counted them right here, right? And then I counted what was going to be made right there. And so for however many of these I have, I make a certain number of these, but for however many of these I have, I make twice as many of those. So these mole numbers had better have a relationship that is equal to the coefficient differential between them on the balanced chemical equation. Does that make sense? We're going to write the combined gas law, then we're going to solve for T2. So it's P1 V1 T1 equals P2 V2 T2, and it'll be T2 is P2 V2 T1 P1 V1. Everybody's got the algebra down, right? Just flip. I mean, that's all that happened, right? If I'm solving for this thing, I need it in the numerator. So how do you get something in a denominator and a numerator? You put it on the other side. So I put that on the other side. Well, I got these things, and they're on the same side as the T2. I need to get rid of them, so I push them to the other side. When I push them to the other side, they go to the bottom. This is on the side that I don't want it on, so I push it to the other side, it goes to the top. That's algebra. Done. What is the final volume of this gas at this temperature going to that temperature and at this pressure going to that pressure? Okay, so I need a volume, so I'm going to write 300 milliliters, and then I'm going to look and see what's going on with this, and I'm going to get a milliliter number out in the end. So, got to do the same thing we always got to do. So 12 and 273, 50 and 273, so 313K, bless you, 582K. All right, so what did the temperature do? It went up. So what would that do to the size of a section of gas? It would increase it. So I'm going to put 313K here and 285K here. You all right with that? Because I increased the temp, so that should increase the size of the gas. What did I do to the gas pressure? I decreased the pressure, so I'm not squishing it as hard. So what's going to happen to it? It gets larger, right? I've got this gas, it's compressed, and I don't compress it as much. I'm not pushing as hard on it, so it's going to get bigger. So then I take these two numbers and I put 360 millimeters of mercury here and 750 millimeters of mercury right here. The millimeter mercury units cancel out, the Kelvin units cancel out, and I'm going to get a number that's considerably larger than 300 milliliters. So 300 times 313 divided by 285 times, wait, what are we doing? I got that, I mixed that up, didn't I? Why didn't somebody stop me? So? Okay, so it definitely got bigger, and it got bigger because it got warmer, and it got bigger because there was less pressure on it. This is what would happen to a hot air balloon as it was rising up into the atmosphere. Does that make sense? As it goes up, it's getting hotter because somebody's using a blowtorch to get hotter, and as it goes up, the atmospheric pressure decreases, so it gets even bigger. So it's a cumulative effect. It's hardest to get the thing off the ground, but once it's off the ground, it's a lot easier to get it floating around because the atmospheric pressure isn't pushing on it as hard. And it might not seem like a big deal, but I mean, you just go up Mount Hood, right? And you definitely feel an atmospheric change. So you elevate past the first 6,000 feet in the atmosphere, you've gotten through most of the atmosphere. Denver is not a good place for people with skin cancer. Does that make sense? Why? There's less filter between you and the sun. If you have skin cancer and you want to be in a sunny place, go to Arizona. Denver would be a terrible place for you to be. There's more sun in Arizona, or there's more sun in Denver than there is in Arizona, and you have less protective coating in Denver. So pressure of the gas is reduced from that to that. The volume of the container is increased by that and that, and I want to know what the final temp is. Okay, so I see a temperature thing. It's units, it's gas stuff, so 110 and 273, so 383 Kelvin. Okay, so I got this thing and it's at 383 Kelvin. So now let's talk about what happens here. If I reduce the pressure, a pressure of a gas is reduced from 1,000 to 750. So what's the relationship between temperature and pressure?
Pressure goes up, temperature goes up.
So it's a direct relationship, right? So what did the pressure do in this problem? It went down. So what's the temperature going to do? Go down. So then I'm going to put the 750 millimeter up here and 1,000 millimeter mercury here. All right, so the volume of the container is increased by moving the piston from 75 to 320 milliliters. So what's the relationship between temperature and volume?
As the volume decreases, the temperature
They're both direct. If you increase the temperature of a balloon, what's the balloon gonna do? It's gonna increase in size. So what happened to this balloon? It got bigger, right? So then what happened to, what must its temperature be doing? The relationship for the temperature is it must be going up. So I'm gonna write 320 milliliters here and 75 milliliters here. In this situation, the volume and the pressure are acting opposed to each other. Are we okay with me saying that? Think about these things being independent of each other. So the pressure is something that's happening related to what the thing that you're looking for is. So I'm looking for temperature, right? So how's the temperature going to be affected if I reduce the pressure? Well, the relationship between those two things is direct. So if the pressure goes down, the temperature should go down. So that's why I've got the pressure units so that I would get a smaller temperature. But the volume got bigger. What's the relationship between volume and temperature? If the volume goes up, then the temperature should go up. So then I use those to put the bigger number on top. These two things are fighting each other though, right?
Yeah.
The pressure should make the temp go down, but the volume is making the temp go up. Doesn't matter. You can do two things at the same time and they'll fight each other, but it'll come to an equilibrium. So somebody have an answer for this one?
1,226. But since you took that into Celsius, right?
Yeah, so guess what answer A is gonna be on a multiple choice test? That number right there. Guess what D is gonna be? Celsius value. So 1226 minus 273. So the answer on it would be 953 K. Ha. Yeah, that's what I meant. C. Are you good with that?
The only thing that I understand the concept of balloon, because the balloon is a volume that can increase, but I'm looking at this like it's inside of an engine and piston moves and it decreases.
The piston increased the size, right? In this case, it got bigger. So it's at this size, and the piston rises.
So
Okay.
there's more room.
So there's more room for it to flow around, but the relationship between the increased size and temperature would be the only reason it would increase in size is because the temp went up. Think about them independent of each other. Yeah.
So can you write them up independently on the board and then show us which things go up and down and then try to explain it for focusing, like write out pressure, temperature, and volume, and then what changes? Goes up and goes down, or yeah.
The only one that's indirect is pressure and volume. All the rest of them are direct.
So meaning that the bigger.
The object is, the lower the pressure is. The smaller the object is, the bigger the pressure is.
So if one would be a bigger, one would be smaller, and so it's like a different thing in that?
Sure,
Yeah.
you can think about it like that.
Like
But-
you say, if it's like the more
but you can't-
something smaller than you get less.
Sure. So if you double the volume of something, but you quadruple the pressure on it, the temperature is going to change by the effect of the temperature. Sorry, the temperature is going to be affected by the pressure change because that was 4 times bigger. And I mean, those things would cancel out and turn into factors, for sure. I don't know if I answered your question. All of these relationships are direct relationships, except for the pressure and volume relationship. That's it. And you should be thinking about the pressure-volume relationship. Has everybody had access, held a syringe? Held a syringe? So if you had a cap on the syringe, what would happen if you tried to push the plunger down? It goes, but as you push, what happens to the force that you need to use on your thumb? More and more force. So the gas is inside that cylinder and you're pushing the plunger down, and as you shrink the size of the gas, what happens to the pressure inside there? It goes up. So I'm squishing this gas. So the volume is now, this was 20 milliliters, now it's only 10 milliliters, and the pressure went up, double whatever it was.
That's what I'm still stuck on, because if you take your syringe and you decrease it by half, so whatever your volume is, you decrease it by half. You increase the pressure.
I know, but that's only one instance. This is two things happening at the same time. So it's not a piston, per se. The temperature of a sample of gas in a steel container it's increased from that, is increased. All right. So this is just, I don't know, whatever. You got to look and see what the heck the temperature units are, right? So this is negative 200 and negative 130. This is still 273 I have to deal with here, right? So this is going to be a Kelvin value of what? 143? 30. No, really? It's
Yeah.
137? 43? There we go. 143K. Excellent. So 143K, and over here this is 2100 degrees Celsius. Are we good with that? And then 273. So 2373K. Awesome. So it's 50 kilopascals, and I want to know what the new pressure inside the tank is. So it's 50 kilopascals. And what did the temperature do? It skyrocketed. So what would that do to pressure?
So is that the same pressure, not temperature?
What?
Or is we looking for pressure?
Yeah, what's the final pressure?
The temperature went way up, the pressure should go way up.
No, it's saying the temperature of a sample in a sealed container at 50 is this.
Okay.
So it's negative 100, it's really cold, and it's at this pressure. And then I increase the temperature dramatically, and so the pressure should increase dramatically. So 50 times 2373, 373, divided by 143, and get 829 kilopascals for my new pressure. Are we good with that?
I think it's 829.7
I didn't get, did I get 7?
829.720.
Oh yeah, I did 7, so it should be 30 with a decimal place.